Hello, this is MAT221, Calculus 1. This is Mrs. Johnson. This is section 4.2, which is in Unit 4, talking about the applications to the derivative. And this particular topic is talking about maximum and minimum values of a function. This is probably the most utilized part of the derivative and applications to the derivative, is where we find the extremes of a function, the maximum and minimum values. So we're going to start with just, say we knew that the mileage of a certain car can be approximated by this given equation, m of v. At what speed should you drive to obtain your best gas mileage? So in other words, we want to optimize or find the maximum gas mileage that will maximize how much I get in miles per gallon. So of course, this isn't entirely realistic, since it's unlikely that we have an equation like this for our particular car. But if we did, we could take this equation and we could solve the problem graphically. We could graph this equation on Mathematica or a graphing calculator, and we would say, okay, the graph looks something like this, where the velocity v is between 0 and 100 miles per hour, for most cars anyway. And we could look and we'd say, okay, well, it looks like right about here is the maximum value of this particular function. So on a TI-83 calculator, we could use the calculate button to remember how to do this. Remember, we would do, right bound, left bound to find the highest value on the calculator. I did it on my TI-89 and actually put it here, but we're also going to do this in Mathematica, this unit. And we could see from the calculator that the maximum value occurs when the x-coordinate is 38.6028 and the y-coordinate is 32.1281. So if v is the velocity in our speed in miles per hour, and our gas mileage is what comes out, this would be 32 miles per gallon, that would be our highest value, or our optimal value. So a car will get approximately 32 miles per gallon if we drive it at around 38.6 miles per hour on average. I want you to notice that at the top of the curve, where we were looking at the maximum, the tangent line to the curve is horizontal there. In other words, it has a slope of 0. And we talked about this a little bit, but we would say, well, notice we're going to use this fact to aid us in finding the minimums and maximum values of a function. In other words, we're finding out that the minimums and maximums are going to occur often when the derivative is equal to 0. Not always, but often where the derivative is equal to 0. So even though the graphing calculator in the computer has eliminated the need to routinely use calculus to graph by hand and to find maximum and minimum values of functions, we still study this method to increase our understanding of functions and mathematics involved. And then what we're going to do is we're going to take that knowledge that we're gaining from some simpler problems and then put them on more complicated problems and use Mathematica to use that understanding that we got to evaluate and to interpret and to analyze curves of more complicated functions. So absolute extreme values are the definition of either a maximum or minimum point on a curve. They are sometimes called global extremes. The global extreme, the global minimum, the global maximum, the absolute minimum are the highest and lowest values that a function will attain in a given domain region. These are also sometimes called absolute extrema. It comes from the plural of the Latin extreme. So Extreme values can be either in the interior or at the endpoints of a function, depending on the function that we're talking about. The absolute extremes, the absolute maximum and the absolute minimum value of a function, there is only one of them. Because remember, the absolute maximum is what is the absolute highest y value or output value that a function will attain, or the absolute minimum is the absolute lowest output or y value that the function will attain. Now, if I looked at this function, y equals x squared, classic parabola, and I looked in the domain from negative infinity to infinity, I notice that this function has an absolute minimum. The absolute minimum value is 0, occurring at 0. And I want you guys to understand and listen to the interpretation here. The absolute minimum value is the output value, which is 0. And then we say, where does it occur? And we say, well, it occurs at x equals 0. What about the maximum value? We say this function has no absolute maximum value because the curve in both directions from going to negative infinity and positive infinity, as the input goes to positive and negative infinity, the output is tending toward infinity or extremely large numbers. So there's no definite, exact highest value of this function. We can say the function tends to infinity, but there's no absolute maximum. There's no highest value that this function will ever attain. However, there is an absolute minimum value. Absolute minimums and maximums on functions, there is only one highest value and one lowest value. However, the value can occur more than once. For instance, if you think of a sine curve, think of a sine curve going up and down. The absolute maximum is 1, but it occurs lots of times. The absolute minimum is -1, but again, it occurs lots of times. But we say that the absolute maximum and absolute minimum, there's only one output value that is the highest and one output value that is the lowest, but those values can occur more than once. Let's change our domain here and look at the domain of this function and now close the domain, and we're only looking from 0 to 2 on this function. Now we can say the absolute minimum value is 0, occurring at 0, and the absolute maximum value of this function is 4, occurring at x equals 2. Again, I want you to notice how we claim these minimum and maximum values. They are the output value of the function, and then we say where they occur as in the input. What about if I change my domain again and say, okay, what about if I look at this domain and say, now I'm looking from 0 to 2, but I'm not including 0 in my domain. I have now no minimum value. Now it looks as though I should have one, but because of the fact of that I never reach this value down here, I'm just aiming really close to it. Okay, is my output value 0.1? Is my output value 0.01? Is my output value 0.001? Is my output value 0.0001? Notice I'm not sure. It's getting infinitesimally close to 0, but doesn't reach 0. So therefore, I don't have an absolute minimum value. There's no exact minimum value or lowest value for this function. However, there is an absolute maximum. It is still, the absolute maximum is 4, occurring when x equals 2. And then lastly, if we open up the domain and have no endpoints on this interval, I have no minimum value and no absolute maximum value because of the fact that those endpoints are not included. Which leads us to the extreme value theorem. The extreme value theorem says this: if a function f is continuous over a closed interval, then the function has to have an absolute maximum and an absolute minimum value over that interval. So the extreme value theorem was pretty powerful when Newton and Leibniz actually proved it and stated it back in the late 16, early 1700s. But its hypothesis is pretty powerful too. The function has to be continuous, so that means it has no holes or jumps or anything like that. And I have to have a closed interval. In other words, I can't look at an open interval with no endpoints. It has to have endpoints on its interval. What the extreme value theorem says is it's simply saying that you're guaranteed to have extremes. That's why it's called the extreme value theorem. I'm guaranteed to have an extreme. So our extremes can occur so that the maximum and minimum point are in the inside of the interval or in the interior of the interval. So say this has a function. Notice I have a closed domain. So here's an endpoint and here's an endpoint. Here's my global maximum value. Here's my global minimum value. So in this case, I could have my maximum and minimum occur in the inside of the interval or not at the endpoints. Or I could have a function that looks like this. I have a closed interval and a continuous function. My maximum actually occurs at one endpoint and my minimum occurs at the other endpoint. Or we could have something like this where, in this case, my maximum occurs at the interior point of the function, inside the function, in the interval. And my minimum point, my absolute minimum point, occurs actually at an endpoint. And we could have all different scenarios of those different values. So the extreme value theorem simply says to us, if you have a continuous function over a closed interval, you are guaranteed to have an absolute maximum and an absolute minimum value over that interval. A little bit more with vocabulary here. We'll talk about local extreme values. A local extreme value is a maximum value within some open interval. And a local minimum value is a minimum value within, again, some open interval. Now, Leibniz and Newton on purpose made this kind of ambiguous. In other words, in a given neighborhood, there might be a value that is highest or higher than the points around it, or lower than the points around it. But again, the open interval is ambiguous depending on what the function is. So let's look at this function. This function has endpoints, so I have an endpoint down here, a left endpoint, and I have a right endpoint over here. Let's look at all the different values on this function and just using some vocabulary. We could say this endpoint over here is the global minimum or the absolute minimum value. It is the lowest value, that output value that this function attains. But notice that this value is also lowest or lower than the points in its neighborhood in this small interval. So every global extreme is also considered a local extreme. It is the absolute minimum value, but it's also a local minimum because it's smaller than the points around it. If I look at this point on the curve, I notice it is higher than the points around it, but it is not the highest point, as this point is. So this one we would say is a local maximum. This point on the curve, we could say, is lower than the points in its neighborhood or lower than the points around it. So we would call it a local minimum, but it is not the absolute minimum because it's not the lowest output value that the curve attains. Next, I notice here is the global or absolute maximum value, and also because it is higher than the points in its neighborhood, we could also call it a local maximum. And lastly, at this endpoint, this is considered a local minimum because, again, the output is lowest or lower than the points in its neighborhood or in the surrounding points near it. So we're going to take these concepts. Right now we're just pointing and labeling, saying what we think they are by just visualizing it and looking at it. But then we're going to come up with ways using calculus to actually find these values.